Today we're going to talk about temperature conversions and density. There are three temperature scales which I'm sure you know: Fahrenheit, Celsius, and Kelvin. Fahrenheit and Celsius both have a degree sign in their symbols. Kelvin is simply a capital K, no degree sign. There are two equations that we will be using in order to convert between temperature scales. The first one helps us convert between degrees Fahrenheit and Celsius and looks like this. Degrees Fahrenheit is equal to 1.8 times the degrees Celsius plus 32. This is written in the format of y equals mx plus b, which is our slope-intercept form back from your algebra class. What we can gather from this then is that 1.8 is your slope and 32 is your y-intercept. What that means for us then is when we have 0 degrees Celsius, we have 32 degrees Fahrenheit. This is where water freezes. Our second equation helps us get between Celsius and Kelvin. Unfortunately, there is no equation between Fahrenheit and Kelvin. If we run into a problem like that, we have to use both equations. And I will show you an example of the Fahrenheit to Celsius in the next slide. Anyway, the Kelvin to Celsius equation looks like this. Kelvin is equal to the degrees Celsius plus 273. Now, you're probably wondering, where does that 273 come from? This is where it comes from. There was a scientist named Lord Kelvin, and he studied the effect of the volume of a gas by its temperature in degrees Celsius. And what he noticed was there was a direct relationship between the two. And the temperature, as the temperature increased, the volume of a gas increased. And Lord Kelvin questioned what happens, or at what temperature then would the volume of a gas reach 0 degrees, reach 0 volume. So let me extend my x-axis. And when he extrapolated the data from his line, he found that the volume of a gas would be 0 at negative 273 degrees Celsius. Now that's an ugly number. Nobody wants to deal with a negative 273 degrees Celsius value. So what they did was they converted this to 0 Kelvin when they devised the Kelvin temperature scale. What's important about this value is we call this number here, 0 Kelvin, absolute zero. We have actually theorized that this is where all motion in matter stops. I'm sure you recall from your grade school science that the particles in a solid are in constant motion and vibrating in place. Well, at the atomic level, the protons, the neutrons, and the electrons are all in motion. At absolute zero, it is theorized that that motion stops as well. We've never actually reached absolute zero. We've come extremely close, but we have yet to reach this temperature. Let's take a look at this example. The high temperature for today is 76 degrees Fahrenheit. What is the temperature in degrees Celsius? Whenever we run one of these problems or complete a problem like this, we always want to write the equation first. So since we're converting from Fahrenheit to Celsius, we need to start with the Fahrenheit-Celsius equation. So we write degrees Fahrenheit is equal to 1.8 times the degrees Celsius plus 32. Now we have Fahrenheit, we need Celsius. So we're going to plug in 76 where we see degrees F. So 76 is equal to 1.8 times degrees C plus 32. Now it's time for our algebra skills to kick in. We've got to solve for C. So we subtract both sides. We subtract 32 from both sides, excuse me. And we get 44 equals 1.8 times the degrees Celsius. How do we get degrees Celsius by itself? If you said divide by 1.8, you're absolutely correct. When we do this, we get 24.4, or 24 equals the degrees Celsius. Now, we've been working really hard learning our significant figures. When we're talking about temperature, we need to be a bit realistic in terms of what we can actually measure. And while our calculator answer may be 24.4, we really want to report a whole number if we can. You have to think about what a bank screen would show us as we're driving down the street. And in Europe, you're not going to get a temperature of 24.4 degrees Celsius. Just like we wouldn't drive down the street and get a report that it's 76.2 degrees Celsius. So we kind of look the other way with significant figures when we are measuring with temperature. I'm not going to give any other examples because the other examples that we would run into would be straight plug and chug problems for the equations. This example is the only one in which you would have to rearrange the equation, so I wanted to make sure we discussed that in class.